electrostatics. This video will be on continuous charge distribution, different types, and then Gaussian surface. So to start with the video, let me refresh your memory, just talking about electric field or anything that related with point charges. We basically deal with point charges when deriving this kind of quantities like electric field or electric force. But in reality, what happens is that the charges are actually continuous, just like those of in a river. Depending on the dimension, this continuous distribution of charges are in the three types. They are linear, surface, and volume charge distribution. Linear means one-dimensional, surface means two-dimensional, and volume means three-dimensional. So we get the point that the charge is continuously distributed, just like that of water in a river, and we have three types: linear, surface, and volume. So what's linear charge distribution? So basically, this is dealing with one dimension, and we have a quantity designated by lambda, which is defined as charge per length. And in this expression, we have seen that this lambda is equal to Q by L, where Q is the charge within a one-dimensional object, and preferably take a very thin wire, because a thin wire usually have only one dimension of its length. So charge density, linear charge density lambda is equal to Q by L, charge per length. And as described here, this L is the length of the wire, and Q is also inside the wire. Then to understand the continuous charge distribution, let us take a small length, say dl, and in that case the charge within this length dl will be lambda into dl, because lambda is charge spanning length, and we'll multiply lambda with dl, and it will give us charge within the length dl. Next, since we are getting a charge within the small element dl, so when we talk about the total charge within the whole length, then we have to integrate, and integrating it will get this lambda l, and the limits for this will be 0 to capital L, where 0 is the minimum length of the wire, and then capital is the maximum length of the wire. So this ultimately gives us the concept of lambda, or the definition of lambda is revived, or what we expect actually. So next, let's start into surface charge distribution, where we use a symbol sigma to understand surface charge density. Sigma is nothing, is the charge per area. Sigma is Q by S, that gives the charge within the surface, and then S is the area of the surface. So two-dimensional means it's of the size of the surface, and that's why we take the surface. In the same way, within the surface, we take a very small element ds, and then we calculate the charge within that element ds. By definition, this will be sigma into ds, because sigma means charge per unit area. So sigma into ds represents the charge within that small surface area. And when over the whole surface we want to calculate the charge, we have to integrate, and while integrating is sigma ds, and the alternate real sigmas, and it is also as expected, because if we compare this case, the sigma s is actually equal to capital Q, and thus this sigma s is capital Q, we can get it from here also, these questions. So this is well obvious now that our conception of whether linear charge distribution or surface distribution can be revived back when we place it in a continuous distribution of charges. And the limits being 0 to s as it should be, because the small element, the small area will be 0, and the maximum area will be s. So this is all about surface charge distribution. Next it comes volume charge distribution. So it's a c-dimensional object like a cube or cuboid, and you can define a quantity rho. Rho means volume charge density, and it's Q by capital V. So Q means the total charge within that volume, and V means the area of that particular volume. Now within that particular volume V, or that particular system, suppose Q, you take a small volume element dV, and in the same way charge within that volume element will be dV into rho into dV, because rho is charge per unit volume. So rho into dV means charge within that small element of volume dV. Now for a whole volume, if you want to calculate the charge, again you get just like a linear charge distribution and surface charge distribution, and you get back this result rho B, and this rho B is nothing but total charge within the volume, and this rho B is equal to capital Q, and we get back this particular relation rho equal to Q by V, and here also rho B is equal to capital Q, and this is also as expected, and we write back all the definitions of lambda, sigma, and rho, and the limits as usual we take minimum 0 and maximum V for a volume element. So coming to the point that now that we have when we talk about linear charge distribution, we talk about lambda, linear charge density, charge per unit length. Coming back to two-dimensional surface charge distribution, we talk about sigma, surface charge density, and its charge per unit area, and then coming back to rho, that means volume charge density, is charge per unit volume. So in every cases, we get the particular definitions of lambda, sigma, and rho whenever we take a continuous integration process. So this all about some definitions and different types of continuous charge distribution. And then it's a very important thing related to continuous charge distribution, which is we'll talk about the Gaussian surface. Actually, this Gaussian surface is nothing; it's related with Gauss law, and it's an imaginary surface. It's striking because for mathematical convenience, we use this surface to calculate or to apply the Gauss law, and where we can find that the both field and the angle between the field and the normal of the surface are constant. This is one of the important things regarding the Gaussian surface. So, if to define a Gaussian surface, you must take that it's an imaginary surface which defines the Gauss law, and to calculate or something or to apply Gauss law, you must have to use this imaginary surface. So, there are necessary conditions for Gauss law. This one is uniformly charged spherical charge distribution. The second one is symmetrical Gaussian surface, and these conditions must always preserved in the Gaussian surface to apply Gaussian law. And the symmetries are cylindrical symmetry, planar symmetry, and spherical symmetry. With obvious examples, we all understand about the cylindrical symmetry, which would take the case of an infinite long wire or infinitely long cylindrical wire, then planar symmetry with respect to a sheet of charge, and then spherical symmetry with respect to a solid sphere. Now we calculate all these things, and we'll apply Gauss law there, and we'll understand what kind of surfaces we require regarding the different kind of such distributions. So this is all about Gaussian surface. So to conclude regarding Gaussian surface, it's an imaginary surface for mathematical convenience of bringing where we apply the Gauss law. It contains certain symmetries like this: cylindrical, planar, and spherical, and the necessary conditions of the uniform spherical charge distribution and symmetrical Gaussian surface. So we must remember that it's not a physical surface, but the thing is that it's very important to calculate certain things with the help of Gaussian law. It's not possible to use the Gauss law with the absence of Gaussian surface. So this is some kind of self-assessment. What is continuous charge distribution? How it differs from point charge distribution, the discrete charge distribution. Define linear charge surfaces, volume charge densities, that is lambda, sigma, and rho. And what is Gaussian surface? Discuss the different symmetries of Gaussian surface. This is all being included in this video. You can take a self-assessment and find that yes, you are understanding all about this different types of continuous charge distribution as well as Gaussian surface. So thank you very much. Hope that the video is useful for you. Thank you.